Thus far in this course, we've considered circuit analysis based on time harmonic analysis on the sinusoids as being the fundamental signal. And we've gone through, and everything that we've described mathematically has been complex because of this. Magnitudes, so voltages were the magnitude of the sinusoid, and the phase of these complex values represented the phase of the relative phase of the sinusoid. Likewise, we had impedances then that were complex value. Everything's been time harmonic analysis, a signal, a sinusoid of some frequency omega. Yet, from a practical sense, if we're doing radio engineering or sensing, electromagnetic sensing of any kind, transmitting and receiving sinusoids, moving sinusoids around from one place to the other is really not very helpful. What we want to do, of course, is to be able to move information from one point to another. To do that, we start with the sinusoid and then we glue information onto it. And we do that via means of modulation. We change either the magnitude and or the phase of that sinusoid in a way which is an analog of whatever information we're trying to send. It might be data, it might be an analog of voice or music or something like that. At any rate, we have to go through and put the information onto our sinusoid by means of modulation. Now, this does not come without a cost. Anytime we take a pure tone, a pure sine wave at one precise frequency, and then we begin to modulate it either with respect to its magnitude or its phase, we find that the bandwidth of that signal will widen. Essentially, a pure tone has a bandwidth of 0. It's a pure tone. It can be described, it exists at one precise frequency, omega. But when we start to modulate it, we find that the energy of that spectrum will begin to spread out. Essentially, from a Fourier standpoint, our signal now becomes not a single sinusoid, but a cluster of sinusoids, all centered around one frequency, close to that frequency, but none of them exactly that frequency. And so we get a bandwidth. An example of that is FM radio. And again, I use FM radio stations as an example throughout this course. The primary radio station I use is a radio station out of Kansas City, 101 The Fox. And their carrier frequency, the eigenfunction provided to them by the FCC, is 101.1 megahertz, 101.1 million cycles per second. That is the sine wave that they transmit. But of course, it's not quite a sine wave because they have to apply the voice that's associated with their station, the music if it's playing, or a Chiefs game if it's being broadcast. They have to glue that onto that signal. In their case, the means of doing that is frequency modulation. And so the audio then is transposed into a change in the frequency, a slight change in the frequency, one that's analogous with the pressure wave that defines the sound, the audio that they want to produce on the other end at your speaker in your car, for example. When they do that, the signal spreads out. For FM radio, the FCC is very clear. The bandwidth needs to remain within 200 kilohertz, plus or minus 100 kilohertz roughly. And so instead of a pure tone at exactly 101.1, we find that the transmit signal is a cluster of tones centered at 101.1 megahertz, but really extending from 101.0 to 101.2, a frequency band of 200 kilohertz. Now, 200 kilohertz is a pretty small bandwidth percentage-wise compared to the center frequency of 101.1. But the fact that we have a bandwidth then becomes a problem with respect to our filters, specifically with respect to our phase delay. If this signal passes through a filter, we want the signal at the other end to be essentially the same signal as at the beginning. We don't want the filter to distort that signal in any way. Now, how could this filter distort the signal? It's a linear device. It can distort it by means of a phenomenon called dispersion. It is a linear distortion. And what happens is that each frequency that makes up the transmitted signal is centered at 101.1, the FM modulated signal. Each of the little sine waves that's centered around 101.1 from, again, 101.0 to 101.2, each of those has to travel through the filter at precisely the same velocity. We want the signal at the output to be a perfectly shifted version of the signal at the input, but it cannot be if each frequency component of that signal propagates through the filter at a different velocity. If each sine wave that makes up that spectrum propagates such that the delay from one end to the other is different, when they add back together at the output, so to speak, we'll find that we have a distorted signal. Every frequency needs to propagate at the same speed. Every frequency of that transmitted signal needs to have the same delay. In other words, we want the phase delay of our filter to be constant across the bandwidth of that signal. If it doesn't occur, we get, again, a phenomenon called signal dispersion, and it causes a signal distortion. And so we want to avoid signal dispersion, of course, if we are to listen to the output of a radio station with good fidelity. Now you might conclude then that we need to design filters such that the phase delay is a perfect constant across the entire bandwidth of the filter. Every frequency that comprises the passband of that filter needs to have a phase delay which is the same as every other frequency. And of course, that would certainly eliminate the problem of signal dispersion and the distortion that it creates. But it turns out that's not really necessary to have a constant delay across the entire bandwidth, which is good news because building a filter with a constant delay across the entire bandwidth is difficult and puts other constraints on filter performance. So let's look specifically at the bandwidth of our transmit signal if we have an FM radio transmitter. Again, we're going to look specifically at the bandwidth of the signal, not of the filter itself. We know in the United States the FM band is, each signal has a bandwidth that's limited to 200 kilohertz. And if you look at this plot right here, this is a spectrum analysis of an FM radio station. This is power, is the vertical scale, and the horizontal scale is frequency. And notice the scale goes from 94.5 megahertz to 95 megahertz. What we see is that the energy peaks at about 94.7. And that is the center frequency. That is the carrier frequency of an FM radio station. So the FM radio station would probably advertise itself as being at 94.7 on the dial, on the FM dial. If you look at the energy, then, though it's not, again, aligned exactly at 94.7, the energy is spread around 94.7, all the way down almost to 94.6, and then almost all the way up to 94.8. In other words, a spectrum, a bandwidth of about 200 kilohertz. Centered at 94.7, the energy is spread from approximately 94.6 to 94.8. And that's typically, again, what we see for an FM radio station. So if we were to look at, on a spectrum analyzer, the spectrum of 101, the Fox, 101.1 megahertz, we would see something like this. Again, this is the horizontal axis is in frequency, and here again frequency is in hertz, cycles per second. In this case, we'll say it's megahertz, since the FM dial goes from 88 to 108 megahertz. The Fox is centered at 101.1 megahertz. If nothing is going on at the radio station, no one is saying anything, no music's being played, we have dead air. In fact, it would transmit a sinusoid, a pure tone, at exactly 101.1 megahertz. But then if we start to play some music or the commercial comes on, that frequency begins to be modulated. And we see then that it wiggles around 101.1, and we start to see a spectral spread that occurs. And again, that bandwidth for an FM radio station is about 200 kilohertz. All right, so what does this mean for us with respect to dispersion and the phase delay of a filter? Let's consider this signal if it resides completely within the passband of some filter. All right, so look at this plot here, and you have to think about this. The horizontal axis is frequency. I put on that horizontal axis the spectrum of our radio station at 101.1 megahertz. All right, so this is from the previous page. So the blue, as we move up, would have a vertical scale of energy. We also have this plot. This plot is the delay of a filter, the phase delay, as a function of frequency. So once again, the horizontal axis is frequency, but for the red curve, the vertical axis would be delay. Higher values would be longer delay, smaller values would be shorter delay. And we can see the delay of this filter changes over frequency. Finally, we put a third plot in here, a third function of frequency, and that is the power transmission function. And here you can see then this sort of gold-looking curve here maps the passband of the filter. The passband starts about right here and goes up to about right here. All the frequencies further out are in the stop band, likewise further down the stop band. The passband is about 1. The transmission in the stop band is approximately 0. And so we see that our radio station now fits entirely within the passband of this filter. If this signal arrives at the input of this filter, then the energy, all of the energy of the signal would arrive at the output of that filter. It would not be attenuated since it's in the passband. If this signal were to arrive somewhere out here in frequency, then it would be attenuated, it'd be reflected, and none would be absorbed. But it's in the passband, so the signal would pass through the filter, and we'd have no problems. Or would we? Because we look at now the phase delay as a function of frequency, and we see that it changes with respect to frequency. In fact, we see that it changes quite a bit over the bandwidth of this transmitted signal. What we find is that the time it takes for a higher frequency, let's say a frequency component at 101.2 up here at the high end, it would take less time for that component to propagate through the filter than would be, let's say, a different component of our FM signal, a Fourier component at 101.0. That delay is higher, it's longer. And so as we go from lower frequencies to higher frequencies across our spectrum, the delay of each of those frequency components changes from something that is very long or high to something that is lower. Each frequency component will propagate through the filter at a different velocity. Each frequency component of the FM radio station will propagate through that filter with a different delay. As a result, when the signal comes out of the filter, even though all the energy is still there, the frequency components of our signals have been essentially scrambled in terms of their alignment. And so the output signal will be distorted. So this phase delay, of course, is nowhere constant with respect to frequency. And we are seeing dispersion as a result. It's important, however, to note that the reason that we have distortion due to signal dispersion is not because the delay, the phase delay of the filter, changes as a function of frequency across the bandwidth of the filter. The problem is that the delay, the phase delay, changes as a function of frequency across the bandwidth of the signal. The signal itself cares not at all about what happens with the phase delay out here at higher frequencies or back here at lower frequencies. In terms of whether it gets distorted or not, it cares about what the phase delay does over the signal bandwidth. So this is a very important distinction. How does it change across the filter bandwidth, the passband of the filter, as compared to how does it change across the signal bandwidth? And again, how does it change across the signal bandwidth is, in fact, really all that's important. So let's look at this situation. Again, we have a filter, the same band pass as we had before. same power transmission function as before. Again, we have our FM radio station centered at 101.1. It's modulated, frequency modulated, so it has a bandwidth, a signal bandwidth of about 200 kilohertz, just like before. The only difference now is the phase delay of this filter is different. The function is different than before as a function of frequency omega. And so we look at this phase delay and we would conclude that the signal at the output of the filter would undergo almost no distortion. That dispersion would not be a significant problem for this particular filter. Why is that? Again, the transmission function is the same as before. The signal passing through it is the same as before. The only thing that's changed is the phase delay. Now, the phase delay is not a constant across the filter bandwidth. Yet, I contend that dispersion would not be a problem here. And why is that? Well, the reason that dispersion is not a problem is because if we look at the delay across the signal bandwidth, not across the filter bandwidth, but across simply the signal bandwidth, we see the delay is approximately constant. The delay for a sinusoidal component at the low end, let's say 101.0, is going to have the same delay as a spectral component at 101.2 on the high end. The delay is the same across the entire signal bandwidth. The propagation velocity through the filter is the same for each component, and so what we'll find is the output of the filter will be precisely the same as the input of the filter, only delayed by some amount. It is delayed from input to output, but it's delayed in a way such that the signal is effectively the same. It's not distorted, just a delayed version of the input. Again, that's not what happens if we have dispersion. Each component is delayed by a different amount, and the signal at the output does not look like a delayed version of the input. It can look like essentially a garbled mess. So let's go back and look at the first example that we did, where this was the phase delay as a function of frequency across the filter bandwidth. And again, it changes across the filter bandwidth just like the previous example did. But in the first case, what we found likewise is the delay changed across the signal bandwidth, and that's the important thing. Again, the delay at a lower frequency is much higher than the delay at a higher frequency component. The delay changes as we move across the signal bandwidth, and that's what causes our dispersion. That's what causes our distortion. So, how much dispersion can we stand? It's impossible to build a filter such that the delay will be precisely the same at every frequency. What we want is a situation where that change in phase delay from one side to the spectrum to the other is made sufficiently small. And of course, this is where we get into problems because we have a lot of subjective terms. How constant is constant? How much dispersion actually results in distortion that is unacceptable. What we find is we can make sort of a heuristic argument here that what we want is a situation where the signal bandwidth in hertz times the delta tau, which is the difference in delay between the highest delay in the spectrum and the lowest delay in the spectrum across the signal spectrum. That delta tau, the product of those two things is much, much less than 1. And of course, this is the kind of thing that students hate when you say it's much, much less than 1, because they want to know exactly how much less than 1. All right, I'll give a rule of thumb out there and say the product of this needs to be less than 0.1. But again, this is completely subjective. It's not like if this value were 0.99, it would be fine. And if it were 0.11, it would be terrible. 0.099, I should say, it would be fine. And 0.11 would be terrible. There's not a, instantaneous transition. Plus, is this sufficient? It may be more than sufficient for your application. It may be horribly insufficient for your application. It all depends on what you're trying to do in some subjective terms of I'm just listening to an FM radio, maybe you could handle more distortion because the human ear or the human brain would not be able to really detect or comprehend the distortion that occurred. On the other hand, if you're sending data across and you're trying to reconstruct some sort of an image, a signal, a piece of software on the other end, that this distortion can cause significant problems if it results in bit error. So it all depends on your application there. So the case where the phase delay across the signal spectrum is relatively constant, while the phase delay across the bandwidth of the filter bandwidth is not constant, can only occur when the signal bandwidth is much smaller than the filter bandwidth. And the examples we've just shown here in the last few pages, that's the situation. The spectrum at 101.1, that 200 kilohertz, was much narrower than the overall passband of the filter. And you might ask yourselves, is that a realistic scenario? Is there ever a situation where that might occur? You might argue that it seemed like the filter bandwidth and the signal bandwidth should be about the same bandwidth. But it turns out there are many cases where a signal will pass through a filter whose bandwidth, whose passband bandwidth, is much wider than the signal bandwidth of that individual signal. And one case of that is FM radio. What we find in our receiver design is that the first signal in FM radio, or the first filter rather, that an FM signal will pass through on an FM radio receiver is something called the preselector filter. Since we know that FM radio extends from 88 to 108, what we do is we build a bandpass filter that will only allow signals through from 88 to 108. We know we're never going to tune to an FM station below 88 megahertz because it doesn't exist. We know we'll never tune to a radio station greater than 108 megahertz because that doesn't exist either. So the first thing is to essentially reject any signal which cannot possibly be a radio station that we're interested in. And so that preselector filter then would have a bandwidth of 20 megahertz. All the FM radio stations in the vicinity will pass through that filter in your radio receiver. But each of those signals, of course, have a bandwidth of 200 kilohertz. In other words, the percentage bandwidth of each signal is simply 1% of the filter bandwidth. In that case, we can have a situation where our delay can change over the preselector bandwidth. We can change over 20 megahertz. But for any individual 20 kilohertz, since it's such a small portion of the overall spectrum, we find the delay changes so little that is insignificant with respect to distortion, or dispersion rather, and thus distortion. So this is the kind of thing you might see in your FM radio. Again, this is the preselector filter right at the beginning, and it's going to pass through different radio stations, 98.1, 101.1, 102.1, 104.3. And notice that most FM radio stations have a number associated with them, and that number is their carrier frequency. That's the frequency of the sinusoid that they are modulating. And again, that gets assigned by the FCC, and they have to use it, and they have to be very precise in how they use it. So a more physical plot of what I just showed on the previous page would be shown here. So this is measurement from a spectrum analyzer. Again, the horizontal axis here is frequency. In this case, it goes from 88 megahertz to 108 megahertz here. And the vertical scale then is energy. And each of these little spikes correspond to a different radio station. Again, this is a spectral analysis. So as we move along in frequency, if we get a spike there that says there's a lot of energy at that frequency, in this case 95.1, which is an FM station. Notice the spike is higher than, let's say, the one at 102.1, and that tells us that the energy that is coming into the spectrum analyzer at 95.1 is bigger than the energy associated with the signal at 102.1. And so this shows a collection of, let's see, what is this, about 7 different radio stations across the FM dial. This happened to be taken in Saskatoon, Saskatchewan, and I assume the Canadian version of the FCC probably follows the same guidelines as the US spectrum, so we don't interfere with each other since we share a common border. But this is the kind of signal, again, that would be passing into the receiver, the front end of receiver of your FM radio. So a pre-selector filter, the example I gave here, again, the bandwidth is 20 megahertz. The center frequency would be about 100 megahertz. So we're talking about a 20% percentage bandwidth filter there, which would be considered to be a wideband filter. And that's what we find for wideband filters. Generally speaking, we don't have to worry as much about dispersion and thus distortion. Now, we can't ignore it entirely, but it is less of a problem for wideband filters. Because for wideband filters, almost certainly we have multiple signals passing through them, like the pre-selector filter, and each of the signals passing through has a much narrower signal spectrum than the bandwidth, the 3 dB bandwidth of the filter over which it's passing. And so let's say this is the delay function with respect to frequency for this particular filter. Again, we see that it's changing over the filter bandwidth, but if we go and look at each individual spectrum and see how much it's changing a little from one side to the other, but it's not changing very much. So little we hope that the effects of dispersion will be minimal and distortion will be negligible, at least not detectable or understandable by the human ear. So for wideband filters, we don't have to worry about dispersion quite as much. The problem really comes in with dispersion is when we consider narrowband signals. So let's look at an alternative situation. In this case, we have a bandpass filter again, and the bandpass filter will allow our radio station at 101.1 megahertz to pass through it completely. But in this case, the bandwidth is very narrow. The center of this bandpass filter is centered right at 101.1 megahertz, and the bandwidth, the 3 dB bandwidth of the passband, is just barely wide enough to allow all of the signal spectrum to pass through. The passband of this filter is approximately 200 kilohertz, maybe a little bit more, 250 kilohertz, something like that. Just wide enough to allow the 200 kilohertz spectrum to pass through the filter completely without being any of it being attenuated. Notice the other radio stations, the one at, let's say, 104.3, none of that spectrum fits in the filter. It lies entirely in the passband of this filter, and so it is rejected, it is attenuated. And very little energy, if any, will reach the output of this filter. The same thing for the radio station at 98.1 and 102.1. This filter allows one signal and one signal only to pass through. And we have these kinds of filters in our radio receiver as well. Ultimately, we can only demodulate one signal at a time. We have to recover the information off the modulated signal using an FM demodulator. But that will only work properly if we present to that demodulator one signal, one FM radio station. And so at some point we have to allow our signal to pass through a narrowband filter, which allows that signal and only that signal to get through while attenuating all others. The analogy I always use is a pre-selector filter is like a big gate that goes into a stadium or a theater or something like that, a big wide open portal where a mass of people can pass through simultaneously. But in the end, you get down to where you have essentially a turnstile. You have something that's just wide enough for one person to pass through at the time. And that is a narrowband filter. And we have an analogous filter to that in our radio receiver. We call it the IF filter. The IF filter is a filter whose bandwidth is just barely big enough to handle the signal bandwidth. In other words, it's just wide enough for one signal, but only one signal, to pass through. Now, what's the problem with this? Well, the problem with this is, again, the phase delay. We might have a situation where the delay, as a function of frequency, is such that it changes across the entire filter bandwidth. For a wideband filter, this is not necessarily a problem because even though it changes across the entire filter bandwidth, it doesn't change, or hopefully won't change very much, across any signal bandwidth. A signal bandwidth which would be a small percentage of the overall filter bandwidth. But for narrowband filters, we assume our signal bandwidth is going to be the same value as our filter bandwidth. And so any filter whose phase delay changes across the filter bandwidth will likewise have a phase delay which changes across our signal bandwidth. Again, for a narrowband filter, we assume only one signal passes through. The filter bandwidth is just wide enough to pass through the spectrum, the signal bandwidth of one signal. And so if the delay changes across the filter bandwidth, then the delay is changing across the signal bandwidth, and vice versa, since the signal bandwidth and filter bandwidth are the same value for these narrowband filters. And so for narrowband filters, we really have to worry about our phase delay. We really have to worry about the effects of distortion and dispersion. And this is a typical rookie mistake when it comes to design. This is where, and I've seen it happen, where engineers will design a narrowband filter for their IF filter that is wide enough for their signal to pass through. They don't care about phase because they thought, well, phase doesn't matter. Well, it does matter. And their phase delays change so much across the signal bandwidth, across the filter bandwidth, that they ended up with dispersion and thus a distorted signal. So you have to be very careful, particularly with your narrowband filters, and make sure that you understand your phase delay. For every filter, really, there are two fundamental functions with respect to frequency. One is the transmission function. That tells us the bandwidth of the passband and how fast a roll-off we have and attenuation of the stop band and such. The other one, though, is the phase delay with respect to frequency. This is one that is far too often ignored by engineers, but ignored at your peril, particularly if you are designing or specifying a narrowband filter. So for narrowband bandpass filters, where the filter bandwidth is approximately the same as the signal bandwidth, to avoid dispersion and the distortion that results, we need to make sure we design or specify a filter whose phase delay is relatively constant across the filter bandwidth. And I say relatively constant. Of course, again, those are weasel words. What does that mean? It's almost impossible, essentially, to build a delay that is perfectly constant, or at least build a filter whose delay is perfectly constant and would be useful to us as a filter. And so we're always going to have some change of delay across the signal bandwidth. The question is it significant enough to cause dispersion or cause significant distortion? Again, that's very much application dependent on what that value should be. But you always have to keep this in mind for whatever application you're designing your receiver for.